remember E by 1 is V1 over F n minus 1, V1 minus V1. Okay? This is the function under V1 over F n minus 1, V1 minus 1. Same idea, function of V1 product rule, hold V1 over F constant, V power n minus 1, differentiate that, you will get a minus 1, plus hold V1 minus V1 constant, differentiate this one, you will need chain rule, so n minus 1, V1 over F, n cancels out, n becomes very large, 1 over n becomes 0, 1 minus 0 is 1, you get 0. So as n goes to infinity, limit n tends to infinity, di star becomes equal to di. You get closer and closer and closer and closer to your valuation. Closer and closer and closer. And remember, it is not because you are bidding a different fraction of your valuation. It's not because of that. It's because as more and more bidders, you are still bidding the same fraction of your valuation. But as more and more bidders are there in the bid, in the auction, every bidder gets pushed, squeezed together. I mean, look at this uniform distribution that we are drawing our bidders from. In this uniform distribution, if there are only 3 bidders, on average they will all lie. If I have more and more and more and more and more and more bidders, then every bidder gets closer and closer to the next bidder. Closer and closer. So when I bid a fraction of my valuation, as you will see in a minute, when I bid the same fraction of my valuation, my bid happens to become larger. Okay? Not because I am bidding a greater fraction, okay, that's an important distinction. I am still bidding the same fraction of my valuation. However, my bid automatically becomes larger when n becomes higher. And this has an important implication for the seller of an auction. So that clearly there is an incentive. If every bidder bids closer and closer to his valuation, when n increases, who benefits from it? The seller benefits. The seller benefits. The seller's revenue from the auction increases. Therefore, it is in the seller's interest, you can see, to get as many people to participate in an auction as possible. Okay? That will drive the bids closer to bidders' valuation. Drive the bids closer to bidders' valuation. Okay? At this point, I can also make in another way. Auction, 2-player first prize seal bid auction. I considered the problem of someone who doesn't know calculus. How does he determine the optimal amount of the bid? And I said to that bidder, no problem. What you do is you assume your bid is the highest, and then you look for the next highest. Then you look for what is the expected next highest, and that happened to be V1. Now I am going to consider the same problem for a bidder in this auction, n bidder case. The question I am answering is, suppose a bidder doesn't know calculus and he comes to me and asks me what is his optimal bidding strategy, what should I answer him, and I am telling you I should answer him this. So say bidder 4 comes to me, bidder 4, he is the one who doesn't know calculus. Out of n bidders, bidder 4 comes to me. I'll tell him, you don't know calculus, that's fine. Assume that you are the highest bidder. I don't care if you are or you are not, but just assume that your valuation is the highest. Assume that your valuation is bidder 4, assume this valuation. Once you have done that, I will tell him, look for the expected next highest valuation. Expected next highest valuation. Whatever the expected next highest valuation is, you bid that amount. Bid that amount. That's what I'll tell you. Okay. The question is, how do I look for the expected next highest valuation? When there was only one bidder here, no problem. I just added up. On average, 0 plus V4 over 2 will lie somewhere here. How many bidders are here now? I have assumed that bidder 4 has the highest valuation, so bidder 4 is standing here. Overall, there were n bidders. There is no one here because bidder 4 by assumption has the highest valuation. Therefore, all other bidders are clustered in this distribution, clustered in this smaller truncated distribution. How many bidders are those? There are n minus 1. Okay? And I am trying to look at the highest of these n minus 1 bidders on average. That is the highest of the n minus 1 bidders on average. Okay, to do that, guys, I will refer you. How do you find the highest in this distribution or the highest in any distribution? I will refer you to page 25. The bottom of page 25 has an expression, has a formula. It's a very important formula, and I will always call it formula number 4. So when I say formula number 4, I mean this particular formula. Okay? And let me explain what the formula means to you. I would like to give you a derivation of the formula, but the mathematics is a bit sophisticated, so I'll ignore it in class. If you're interested in doing the derivation, you can. Formula 4 goes like this. EK is equal to BL plus n plus 1 minus K over n plus 1 BH minus BL. Now, let me explain each of these terms to you. What does this formula say? BL is the lowest value in any uniform distribution. In our case, if you are looking at this whole distribution, then BL is 0. BH is the highest value, the upper bound of the uniform distribution. Here, BH is 1. Okay, BH is 1. That's a BL and BH thing. N represents the size of the sample. So this is the whole population of bidders here. You have drawn n of them randomly out of this population. N of them randomly out of this population to conduct your auction. So n represents how many bidders are there have you drawn from this distribution. That's n. Okay. K represents the term you are looking for. For example, if you are looking for the average highest value in a given distribution, K is equal to 1. Average highest value, K is equal to 1. If you're looking for the average second highest value in the distribution, K is equal to 1. If you're looking for the average third highest value, K is equal to 1. If you're looking for the average lowest value, K is equal to n. N highest value or the lowest value. So K stands for what value are you looking for on average? Highest value, the second highest value or the third highest value? Which highest value are you looking for? Okay. So E1, for example, stands for the average highest value in a sample. Okay, that is drawn from this formula. E2 stands for the average second highest value. E3 stands for the expected third highest value, and so on and so on. And it is very, very important for you to understand what it means to say expected highest value, expected second highest value, expected third highest value is important for you. And understand what's going on. What does it mean to say expected highest value? Now consider these sunglasses that I wanted to auction in lecture, right? Now I have 5 lecture groups. 5 lecture groups. I could auction it in the Monday lecture group, Tuesday lecture group, Wednesday, Thursday, and Friday lecture group. I have 5 lecture groups. And imagine all of these lecture groups have the same number of students, same number of bidders, same number of bidders. And they are all drawn from this distribution. Some distribution between BL and BH, right? Lowest value is BL, highest value is BH. Right? So I have the same number of guys here, same number of guys here, same number of guys here, same number of guys here. So if I ask the Monday group to list down their valuations for this sunglass that I am trying to auction, you will get n different values, right? You will get V1, V2, V3, this is the highest, this is the second highest, all the way till BH. The Tuesday group also similarly will give you a different V1, V2, V3, all the way till BH. Same for the Wednesday group, same for the Thursday group, same for the Friday group. Now notice, the highest valuation in the Monday group, must it be equal to the highest valuation in the Tuesday group? No. They can be different. They can be different. Clearly they can be different. Just one randomly drawn sample. They can be different. But if I add these highest valuations up across all possible groups of n people here and divide by the number of groups here, I will get E1, the expected highest valuation. On average, this is the highest valuation that a bidder in this distribution will have. That's what it means. On average. Similarly, if I add up the B2 and take an average, that will be on average the second highest valuation in this proportion. Okay? This one is the second highest valuation in this sample. Okay, in this sample. But E2 will be the average second highest valuation over the whole population. Of bidder. That's what it is. And this distinction between a sample and a population is very, very crucial for your understanding of auctions. Okay? Later on you will see. So this is what it means by saying expected highest valuation, expected second highest valuation, expected third highest valuation. The expected lowest valuation, we just add up these, divide by n. This will be the n. On average, the nth highest valuation. The nth highest valuation.